Now, if one, if Z naught is a removable singularity, just like we have learned last week. Then f of z is simply equals to the Taylor series. That is, in this case, the principal part n from -1 to minus infinity Cn z minus z naught raised to power is equal to 0. This is the principal part of the Lorentz series. The Lorentz series, this Lorentz series, this Lorentz series, minus infinity to infinity Cn z minus z naught raised to power can be written as summation n from 0 to infinity Cn z minus z naught raised to power n plus summation n from -1 to minus infinity Cn into z minus z naught raised to power n. This part is called the principal part of Lorentz series, whereas this part is called regular part of the Lorentz series. And of course, this one you can still write it to be equals to summation n from 0 to infinity Cn z minus z naught raised to power n plus summation n from 1 to infinity C minus n into z minus z naught raised to power n. That you can still write it like that. And so if z naught is removable, the principal part is equals to 0. This part, this is the principal part, is equal to 0. Now, if z naught is a pole of order n, then f of z is equals to summation n from 0 to infinity. So it will have principal part, regular part, but it will also have principal part, which is k from 1 to n c minus k into z minus z naught raised to power k. So if the pole is of order n,
Okay.
then there will be only n principal parts. It will not be infinity. It will not be infinity, there will be only n principal parts. For 3, if z naught is an essential singularity point, then f of z is simply going to be Lorentz series. So if f of z is if z naught is an essential singularity point, then you have the Lorentz series. So the Lorentz, the principal part also define the behavior of f of z at singularity point. Because if z naught is removable, the principal part will be equals to 0. So we are going to have in that case only the regular part. That is, the principal part will be equals to 0. But if it is z naught is a pole of order n, then we are going to have only n principal parts. But if it is an essential singularity point, then we are going to have the infinite series of analytic function. Definition. Let f of z be analytic in a domain D. Residues are calculated at singularity points. When we talk about residue, we talk about residue as singularity. Then the residue of f of z at z naught, which is inside the domain D, is denoted as res of f at z naught. So the residue of a function is the short form is residue of f at z naught.
Okay.
And this residue of f at z naught is defined as 1 over 2 pi I, the integral over lambda of f of z dz. That is the residue of f at z naught. Is equals to 1 all over 2 pi I, 2 pi I. The integral taking over lambda
Okay.
now. See, we are talking about residue of at z naught, but here you don't see z naught, but z naught is written with this lambda, where lambda is a very small closed contour containing only z naught as the singularity point of f of z.
Okay, sir.
So this lambda is a very small circle that contains only z naught
Okay.
as the singularity point of f of z. Now, remember that in the Lorentz series, we said Cn is equals to Fn in the Lorentz series f of z, which is equals to summation n from minus infinity to infinity Cn at z minus z naught raised to power n. No, this is Lorentz series. We said our Cn is equals to Fn at z naught all over n factorial.
Okay. Yes, sir.
Is that okay? But you know that this one is equals to 1 all over n factorial into n factorial all over 2 pi I integral all over lambda. Let me write it somewhere else. Cn is equals to Fn z naught all over n factorial. That is how to calculate the coefficient of Lorentz series.
Yes.
But this we can write this one, we can write it as 1 all over n factorial Fn at z naught. Is that okay? But this Fn at z naught, you know, this is n derivative. This is by Cauchy integral formula. This one is equals to 1 all over n factorial into this one is n factorial all over 2 pi I integral all over lambda f at z all over z minus z naught raised to power n plus 1 dz. This is the n derivative of Cauchy integral formula.
Yes, sir.
Okay. So which implies that our Cn is equals to n factorial will cancel n factorial. We have 1 over 2 pi I integral all over lambda f of z all over z minus z naught dz. Is that okay?
Yes, sir.
Because this n factorial is cancelled. And from here, we can see that c minus 1, if you put your n is equals to minus 1, you are going to have 1 all over 2 pi I integral all over lambda f of z
All over.
dz. Because if your n is equals to minus 1, it will be 0. So that is 1. So that is what you got. And you know this is now is equals to the residue. This is the residue of f at z naught. So that is the relationship between. That is our residue. that the residue of f at z naught is the same thing as the first coefficient of the Lorentz series. Then you look for the first coefficient of the principal part. That will give you the residue. If z naught is removable, is a removable singularity point, you see that f of z will be equals to summation f from 0 to infinity cn z minus zn. And you see that here there is no principal part, which implies that c minus 1 is equal to 0 here. That's because there is no principal part. And so it implies that residue of f at z naught is equal to 0. So if the singularity point is a removable, residue is equal to 0. Because there will be no principal part.